you have a probability space, you have a Borel set, and you have a probability measure. Oops, what am I doing here? Okay, so this is the probability space. Okay, and then, well, the Borels, that's a little bit like what ends up happening is that you have sets in this probability space. Okay, and this set would be like A. Okay, and the set is a member of the Borels, okay, or the sigma algebra on the probability space. And then this thing here, the probability, this is a function of sets. So it takes as an input a set, and it produces an output of a value R, a real value that's between 1 and 0, okay? So basically the probability is a function which maps the Borels to the real line, actually just the interval 0 to 1. So that's fine. You might say, well, why not just include all subsets of the probability space? And it turns out that you can't do that. Well, you can do that in some special cases, but mostly you can't do that because it causes problems. Because it turns out that if you believe in the axiom of choice, you can construct subsets that are really messed up, and they'll get you into trouble, okay? So if you want to know more details about that, you would take a course in measure theory, right, in real analysis. But what ends up happening is that, so the probability, so this is just a set of subsets, okay? But the Borel is a sigma algebra, so it has the property that for all A and B, which are members of this, then A intersection B is also a member, and A intersection B and A union B is a member. Okay, so it's closed under finite. So if it's closed under one intersection, then it has to be closed under finite intersections because you can just recursively apply. So it's closed under finite. It's actually closed under countably infinite intersections. Okay, and so basically intersections and unions. And then what happens is that so the probability measure has certain properties. One is that the probability of the complete space is 1, okay? The probability of the null set is 0, okay? And then if AN intersection AM is null, is null for all M and N, then the probability of the oh, I'm running out of space here. Okay, I'm sorry. Let me just rewrite this so it's a little bit neater. I hate being sloppy. Okay. P measure. Has a property that the probability of omega is equal to 1. The probability of the null set is equal to 0. You need this. I'm not sure you need that, actually. You might be able to prove it, but it's fine to assume it. And then if you have an infinite sequence of sets, AN, for n stay equal to from 1 to infinity, such that AN intersection AM is null for all M not equal to N. In other words, there are disjoint sets. That's just a complicated way of saying the disjoint sets. That the probability of the union from n equals 1 to infinity of AN is equal to the sum from n equals 1 to infinity of the probability of AN. This has got to be a countable infinity, because otherwise you'd have problems. Like, to me, the most obvious case of where you would have a problem is, let's say you have the real line, okay? So your probability measure is the length of the interval on the real line, right? So the probability, I'm stating that as an assumption. I'm constructing a probability space. So the length of the line is 1. So the omega in this case is the interval from 0 to 1, right? Now, if you take every individual point, the measure of that point is 0, right? But if you take the union of all the points, it's the entire interval. So then you have that sort of what appears to be a contradiction, because you take the sum of a bunch of things that are all 0, and you get something which is equal to 1, right? That should maybe worry you a little bit. So where's the problem? Well, the problem is it's an uncountable sum. It only works if it's a countable sum. If you have an uncountable sum, it doesn't count. You break it, okay? So you can't, I remember asking this of my junior high teacher, and it really got him kind of pissed off. But it actually is a valid question. Okay, so fine. So that's a probability measure. So now that's all good. Now we have a thing called random variables. See, that's like, if you were taking a formal course in probability, this would be the first 2 months of the class, but we just covered it in 15 minutes. So now, random variables, there's enormous confusion about what the difference is between a random variable and a probability space, okay? So they're totally different things, of course. So a random variable is a function, say x, that maps this probability space to the real line. So it would be like x of omega. Only what happens is you never write x of omega. You just write x, okay? And everybody just assumes it's of omega. One of the things that's kind of might be disturbing to you about probability is that it's kind of abstract, because you always assume that there's this underlying probability space, but you never really say what it is, okay? And the reason is you can prove a theorem that you can always construct a probability space for any random variable. So you just kind of assume it's there. But so now what happens is that you can define events. So I can define the event A, which is the set of omega, a member of omega, such that, say, x of omega is less than or equal to lambda. So that's a set in the probability space. So then you can ask yourself, well, what's the probability of that event? So the way we write that is we write the probability of x less than lambda. So when you write this, what you mean is, because it's too much trouble to write this all the time. So you write this, when you write this, the probability that x is less than or equal to lambda, x is a random variable, lambda here is not a random variable. What you're asking is, you're saying, well, what's the probability of the event? Where the event, an event is a subset of omega. So these A's are events. We call these things events. I'll put it in quotes, okay? I mean, event's a nice word because it evokes the right kind of emotional feeling about what you're talking about. But, you know, we could call it anything, I guess. We could call it a lollipop, but it would be confusing if we called it a lollipop. So we call it an event instead. But so this is then this is an event, okay? It's a set of omega such that x of omega is less than or equal to lambda, and then the probability of that event is some number between 0 and 1, right? So that's fine, that's all good, okay? If there's actually one other thing I'm not saying, of course, here, which is that this random variable it can't really just be any function, technically speaking. It's got to be what's called a measurable function, okay? You know, it's like measurable functions are something that only mathematicians care about, okay? Okay, because, I mean, you know, how many people know what the axiom of choice is? Okay, there's at least somebody. Okay, there's a thing called the axiom of choice. So there's like, I think there's like 13 axioms in mathematics, okay? The basic axioms. Those are the ones that you use kind of every day. Like, and things like that the real line is complete, and that there's a identity element for addition, 0, and there's an identity element for multiplication, 1. But then you start getting into weird things, because there's this thing called Girdles' Incompleteness theorem, okay, which is that there was a time when people thought they were going to prove that mathematics was rigorously complete, okay, that it was, that you could prove mathematics was correct, okay? And sort of Girdle blew a hole in that entire concept by proving that for any system of logical system which is more complex than basically something very finite like tic-tac-toe, that you can always find theorems that are neither false nor true, okay? So in other words, they can't be proven false or true. They're just orthogonal to the other assumptions. So you can have an infinite number of axioms, okay? But you know, they get weirder and weirder, okay? So the next most complicated axiom is the axiom of choice, which is the assumption that that if you have a collection of sets, that you can take one element from each set, which seems very reasonable, right? So pretty much most mathematicians accept the axiom of choice as being true. But anything you have to use the axiom of choice to prove, or to prove or construct, is really, you know, you're going out where the buses don't stop, okay? So you've got to have a function which is not measurable. It's a really messed up function, okay? So it's something you're just not going to run into in an engineering context. But it's nice to know that they're out there, okay? And the other thing that's kind of interesting is in the set of all functions, the vast majority of them are all not measurable, okay? So it's a little bit perverse. But anyway, so, okay, I just felt I had to tell you that from the point of view of intellectual honesty. But okay, now that I've said that, it's sort of a disclaimer. It's you know, any reasonable function you're going to ever pick is measurable. So this is any function. So then you can find this set. So then it turns out that this set has to be measurable if that function is measurable. That's basically what it means to be measurable. Okay, fine. So enough said about that. So okay, so now you know what a probability space is, and you know what a random variable is, right? So now it all seems quite abstract, and we have a thing called a cumulative distribution function, right? CDF. Now it's starting to sound more normal. And you say, okay, so fx of lambda is the probability that the random variable x is less than lambda, okay? And this is, the CDF has to have 3 properties. Okay, the first property is that the limit as lambda goes to infinity of fx of lambda equals 1, okay? Because the random variable has to, with probability 1, be less than infinity, okay? Because infinity is not a legitimate value for a random variable. I have this thing goes from omega to r. R doesn't include infinity. You can actually include infinity and minus infinity in the output. I mean, to make those new symbols, but we're not doing that, so this has to be true. And then the limit as lambda goes to minus infinity of fx of lambda is equal to what? 0, right? Now the other thing that has to be true is that, and I always get confused about this, so the function has to, okay, then what has to be true is that also that f of lambda 1 has got to be greater than or equal to f of lambda 2 when lambda 1 is greater than or equal to lambda 2, right? Because, you know, if x is less than lambda 1, if x is less than lambda 2, then x must be less than lambda 1, which means that the event x less than lambda 2 has got to be a subset of x less than lambda 1, right? Right? Yeah. Right. So this has got to be, so consequently what happens is that, okay, one of the properties you can prove of probability is that the probability of the event, if this set is strictly contained within the other, then you can represent this as the union of this and a disjoint set, which is the difference. And then the sum of the two probabilities has to be, something I should have said here, I think, is the probability of A has got to be greater than or equal to 0. I think maybe I can use, I really forget, but those are all true, okay? Maybe you only need that one, and you don't really, you may not need all those axioms. Okay, fine, so you got this, but now what happens is that, so this is monotone increasing, but what can happen is that it might be, so let's say this is -2, and at -2, there's some probability, say 10%, that the random variable is going to equal -2. So it's a discrete probability that it's going to be equal to -2. So what ends up happening is that, how do you do this thing? I'll just turn it like that to get out of the way. So over here, you're going to have a jump. So this thing can't go down. It can only go up monotonically. It can stay level. That's okay. If it stays level, it means that the probability of being anywhere in that interval is 0. But if you have a discrete probability, it's going to take a jump. When you get to that discrete probability, because it's less than or equal, at that point, it takes on the larger value. So this thing always has to have the property that the limit of, I won't even write it. I'll just say it. Must be, this is called right-hand or left-hand continuous. I think it's called right-hand continuous. Yeah, right-hand continuous. Okay, so any probability, any CDF has to have these properties. It has to be, take a limit of 1 in infinity, 0 to -infinity, monotone increasing, and right-hand continuous. Furthermore, it's not just necessary, it's sufficient. So it's not just the case that any CDF must have these properties. It's also the case that anything that has these properties must be a CDF. Okay, so it's if and only if. So what do I mean by that? I mean, if you give me a cumulative probability distribution of this form that has these 4 properties, I can construct a random variable with that distribution, with that CDF, okay? And that's, I think, problem 1 in the homework. Is that problem 1 or 2? The infamous problem 2 in the homework, okay? Now, it turns out that solving problem 2 is kind of tricky. Solving it completely is kind of tricky, okay? But solving a sort of a subcase of it that gives you 90% of the intuition isn't so hard, okay? The thing that makes problem 2 hard is that these discontinuities, okay? But if you assume that the CDF is continuous, okay? So if CDF is continuous, then there exists, that means there exists. A backward E means there exists. How many people know that a backwards E means there exists? Okay, most, okay, but not all. By the way, that means there exists. I don't need this anymore, right? I don't care what Purdue's administration says. Actually, that's really true. I like blackboards, okay? I mean, okay, I don't know how you guys feel about them, but I'm sorry, I like them, okay? What was I actually thinking right then? Oh, I wanted to write, this means there exists and this means for all. I think the blackboard was one of the greatest inventions of all time. Actually, I once was in Copenhagen, and I was at the Niels Bohr Institute, and I went in and it's like where, I guess, Niels Bohr or Heisenberg was lecturing, and they had pictures up on the wall. It was pretty cool. And they had this very complex system of blackboards that like went up. It was like a Rubik's Cube of blackboards. Okay, that means for all. So if we have, there exists an x such that for all y, we have like f, okay, this, don't confuse this p with the other p. We have p of xy. P of xy means that some property of xy holds, right? So this is standard logical notation. It means that I can find some x such that for all values of y, some property holds jointly between x and y, okay? So logic is very important in engineering, in my opinion. Okay, so if the CDF is a continuous function, then there exists a function f inverse x of whatever, of y. And the idea is that f inverse x of f, right? In other words, you can't always invert every function. But if a function is continuous and monotone increasing, then you can invert it, okay? Intuitively, what would happen is that you have say x and y, and you have some kind of function. And if you take x and y in a plot and you flip them, right? If this is a piece of paper, you'd literally just flip it, right? Then that's the inverse function. Now the problem is if it's not a monotonely increasing function, then when you flip the axes, the function will no longer be unique. It won't have, you'll have a problem, okay? So it doesn't always work out, but as long as it's monotone increasing, it works out. And then the solution, so the solution to problem 2 is that it turns out if you have a random variable u, which is uniform, obviously I haven't really got, okay, uniform on 0, 1, this is a little bit of a tangent because I'm talking about problem 2, okay? So I'll put here problem 2, okay? Then it turns out that if we define y, or we define x, this is a random variable, to be equal to f inverse x of u, it turns out that that random variable has the cumulative distribution of f of x. I mean, it's actually, it may look a little abstract, but it's pretty easy to prove, okay? It's tricky to prove when you have discontinuities, but if you don't have a discontinuity. And this is a practical thing, because in a computer, this tells you how you generate random variables with a specified distribution. What you do is you calculate their cumulative distribution function, you calculate the inverse of the cumulative distribution function, and then you generate a uniformly distributed random variable on the interval 0 to 1, and you put that uniformly distributed random variable into the inverse probability distribution, cumulative distribution function. By the way, you might say, well, how am I going to generate the uniform random variable? Well, it turns out there's a lot of numerical methods for generating uniformly distributed pseudorandom variables. Basically, you just generate sequences of independent binary values, and you interpret them as like as fixed point value representations of binary numbers, okay? Is there any questions about this? Are you following this? Am I confusing you? Okay. All right, good. All right, so that's just problem 2, okay? So, and this is going to be really important because, by the way, you might say, well, sometimes you can't compute an analytical expression for the cumulative distribution functions inverse. For a lot of distributions, you can. An example of one where you can't do it very easily is the Gaussian, because the cumulative distribution function for the Gaussian is a thing called the error function, okay? Yeah, and it doesn't have closed form. But there's a trick to that. What you do is you can actually, in 2 dimensions, you do it as, okay, I won't give you the trick. But the point is that you can do it. It's not that hard. But my point is just that this is sometimes a tricky issue. And later on in the class, when we talk about stochastic simulation, it's a fundamental technique for generating random variables with arbitrary distributions, okay? So, so that comes back as a recurring theme. Okay, now, okay, so we know about cumulative distribution. Now, every random variable has a cumulative distribution, okay? Every random variable has a cumulative distribution. But I'm sure, as you all know, because all this stuff I'm telling you is sort of abstract, but you kind of know it already because you've already taken probability. In one way, you should perform somewhere, right? But so then we have a thing called a probability density. Which is what you probably usually use, and is also what we'll mostly use in this class, okay? Now the probability density, P of x, okay? The idea is that this is supposed to be the derivative Okay, first of all, I have to make a little side trip here, and I wrote fx of lambda. I put a lambda here because what will end up happening is so this thing is the probability that x is less than or equal to lambda, right? I use the lambda because what often happens is people will write f of little x here, and they'll use a little x, and that's supposed to tell you that this is the cumulative distribution of the random variable uppercase x. At least in the beginning of the class, I'll try to remember to use uppercase letters for random variables, okay, and lowercase letters for things that aren't random variables. Okay, which begs the question, what's a random variable? We already answered that question, but I'm sure you've forgotten by now. So, what's a random variable, okay? Okay, let's go back and remember. It's the simple things in life that are tricky, okay? So what's a random variable? A random variable is a function, x of omega, right? Yes?
You can't see yourself on the camera.
Oh, am I actually off? There you go, interesting. Oh, interesting, okay. Can you see the board here?
No.
Oh, I aimed the thing wrong, okay. Okay, so I'll come over here. That's good. Thank you for the alert. Okay, so a random variable is a mapping from omega to r. A number, on the other hand, is just a member of r. Now, it's a confusing issue because we just write x. Nobody ever writes x of omega, okay? So somebody's got to tell you when they write x, this is a random variable, okay? And here's the thing. It's like one of those things where, you know, your parents will say, oh, could you take out the trash? And just a minute, you know, and then they come back and you say, like, did you take out the trash? Oh, I forgot, okay? You know, you always forget the things where, you know, it's sort of a little advantageous to forget, okay? Of course, you'd never do that on purpose, right? But it's the same thing here. You pretend to forget that you weren't sure if it was a random variable sometimes. Because then sometimes you're like, it's a random variable. No, I mean it was a number, okay? Like you can sort of change, all the equations are sort of still true. You just plug a random, you just reimagine the same equations with it of being a random variable. But it's important to also be very precise, okay? They say sometimes you have to be very clear, okay? Is this thing a random variable? Is it a number, okay? So I call this a number because it's just a regular variable. So if it's a random, so one thing to remember is the expectation of x, that is just a number. That is not a random variable, okay? The expectation of x is not a random variable. Okay. So this thing is not a random variable. Now, when I say it's not a random variable, I actually could plug a random variable into that function. You know, you can plug a random variable to any function. By the way, if you have any function, let's say you have some function of a random variable. Is a function of a random variable a random variable? The answer is yes. If you've taken any other course I ever teach, I always go over this very carefully. So this is a random variable. Any function is a random variable is a random variable. So like for instance, let's say I flip a coin, and then I use the outcome of the coin flip as my input to some function, like to decide whether or not I'm going to leave the room. So then if flipping the coin is a random variable, whether or not I'm in the room is also a random variable because it's a function of a random variable. So any function of a random variable is a random variable. The expectation of any random variable is not a random variable, it's a number, okay? So people do this, but it's bad notation. That said, I'll probably do it too, okay? But it's okay to abuse notation once you fully understand exactly what you're doing. So I put a lambda in here to emphasize the fact that this thing is not the same as x. But I'll use a lowercase x here. So here I have to be careful. This is the probability distribution. The subscript here, x, means that it's the probability distribution of the random variable x. But this is just anything. I could have put any other random variable. I could have just put like a little happy face in here. Okay? I can use any variable I want because it's a dummy variable in the function. I can use any variable. So this is x. This is x, okay? Okay, now, then what happens is that the probability that x is less than or equal to lambda is equal to the integral from minus infinity to lambda of px of little x dx. Okay, and that's hopefully now starting to look a little more familiar. The problem is this doesn't always work, okay? This doesn't always work. It doesn't work for a number of reasons. One reason it doesn't always work is that the function might not be continuous. If the function isn't continuous, you can't differentiate it, right? But you can differentiate a function. Okay, so you have the function like this. Okay, so over here, the probability distribution would be like this, and then maybe it would be like this, I don't know. But over here, you're going to have a spike in the density associated with the discontinuity, because there's a discrete probability that it takes on that specific value. So engineers would be like, why are you giving me a hard time about this? I'm just going to put a delta function here, right? So this will call that value x0. So this will be like delta of x minus x0. This is x, okay? So you'd say, what's the big problem? Well, it turns out that the probability distributions that are continuous would still have the property that the probability density doesn't integrate to the probability of being in the interval, okay? So the classic function, which I won't spend too much time on here, is the so-called Cantor function. So what you do is you take the interval from 0 to 1, and you, this is 1. So at the point 1/2, you put this thing here like that, okay? So in this center third, you make it equal to 1/2, right? And then over here in the center third, you make it equal to 1/4. And over here in the center third, you make it equal to 3/4. Do you understand where I'm going with this? So now what you do is you keep taking the center out. It's like cutting out the center of a peanut butter and jelly sandwich or something, okay? And you keep cutting out the center of the part you haven't dealt with and replacing it with the midpoint. If you do that to infinity, what will happen is asymptotically these will get closer and closer together. So asymptotically, in the limit as you go to infinity, this function isn't discontinuous. It's ill-defined at some points that fall that you'll never get to, okay? But those points are essentially what they call a set of measure zero. So you just fill them in. It's like if you had it's like you spackling. Like after you leave, of course these days, I guess, when I was in college, we would put up various things on our wall, and then when we left the room, we'd have to spackle over the holes. Nowadays, you have those special zip things. I forget what they're called, that don't damage the walls, although maybe you still put holes in the walls. If you do, it would be somewhat reassuring for me. I'd feel like there was still hope for humanity. So the thing is that you spackle over those little holes, okay? And then you got a continuous function. But the function's gradient is 0. The function's derivative is 0 almost everywhere. So you have a function which has a derivative of 0 almost everywhere, but it gets from 0 to 1. So it's an example of a function which, for this Cantor function, the probability of this Cantor function, or p of x dx, over any interval, so from 0 to 1, equals 0. Yet it's a legitimate probability distribution. So with probability 1, the random variable takes a value between 0 and 1, but its probability density is 0. So my point is, now this is not quite as bizarre as a non-measurable function, but maybe you don't run into this all the time. But I at least wanted to point out that it exists, okay? So if you're trying to do formal proofs, you use cumulative probability density, cumulative distribution functions, because they always exist. The probability density function does not always exist, even when you fix it up with delta functions. Okay? This is a counterexample to that. So, okay. Now, so now what you have to do is you have to generalize this to multiple dimensions. So then you have a cumulative probability distribution in multiple dimensions. I'll let you read about that, okay? And then you have independent random variables. Okay. So we'll just assume there's a density, even though there isn't always a density. The cumulative distribution function, okay, so then what happens is that, so you have x is like x1 through xp. So so this thing is a member of r to the p. It's a random variable, but it takes values in the set r to the p. Okay, and then the probability density of x, okay, is the derivative, the multidimensional derivative of the cumulative distribution function. I'll let you read about it here. Okay, and if the probability density is equal to p1 of x1 times p2 of x2 through p of xp, then the thing is independent. Okay, It's an independent random, these are independent random variables. I'll let you read about it, okay? Now, if you have the expected value of the sum from n equals 1 to say infinity of xn, that's always equal to the sum from n equals 1 to infinity of the expected value of xn. That's always true. But if you have the expected value of the product from n equals 1 to infinity of xn, that's equal to the product of the expected value of xn from n equals 1 to infinity. This is only when xn are independent. So you can exchange the product and the expectation only when the random variables are independent. But you can always exchange the expectation and the sum. Okay? Everybody's good with that? Now, what else? Okay. Okay, I'll let you read stuff. Okay. Okay, I want to go over this thing. This is kind of a cool idea. We got, I think, what time is it? I'm only trying to figure out what time it is. Okay, this is a complicated way of figuring out what time it is. I'm assuming that my watch is 2 minutes fast. Okay, so if we have the expected value of x given y, what is this? This thing, x is a random variable, y is a random variable. We can have more than one random variable now because we've defined this concept of multidimensional random variables, okay? So x is one component of a random variable and y is another. And so the interpretation of this, okay, so the definition of the concept of a conditional random variable is quite subtle. One of the, the difference between people who understand probability and everybody else, and by the way, the number of people who understand probability is relatively small, is the people who understand probability understand what conditional probability is. This is one of the most fundamental and subtle ideas in probability. Especially if you're talking about estimation, there's massive confusion about what it really means, okay? But the way to think about this is really a function of y, okay? Now, when you're talking about conditional probability, usually what happens is in your undergraduate conditional probability course, they say, well, the conditional probability, what you do is you take, so actually, and more generally, this could be like f of x, right? So what you would do is you take the integral of f of x. Oh, I shouldn't have used that. F, I'll use g, because I use f there. So you have this times the probability, conditional probability. Of course, it begs the question, what's the conditional probability density? If you didn't tell me what the conditional expectation is. Okay, but, and then this gives you some function, f of y, okay? Then this is the same as that. So you take f, and this is like what I was saying. Sometimes you actually put the random variable into the function, the density function. This is a conditional density function. This is the conditional expectation of x given y, and you stick in the random variable there. That's what the conditional expectation is, right? So that's why the conditional expectation is a random variable. Because the thing you're conditioning on is random. Does that make sense? Anyone want to ask a question about that, or does that seem crystal clear? Okay, good. So since the conditional expectation is a random variable, so let me just write here, this is a random variable, since the conditional expectation is a random variable, that means you can take its expectation. So then the conditional expectation of x given y, like this. So then the question is, well, what is the conditional expectation of, what is the expectation of the conditional expectation of x given y? It's a number. That's a true statement, because it's the expectation of something that has to be a number, right? But what specific number is it? And by the way, this is proof that it's the simple things in life that are really important, okay? Because this is such a simple idea, okay? Yet it's so powerful. Yeah.
6-1?
Yeah, sort of, but not at all. Close. I mean, you're on the right track, in a sense. So if I say, this is the expected value, so this is my expected height, given that it's like, that I'm 15 years old, okay? Huh? It's the expectation of x. Because this says, what's my expected height if I'm 15 years old, if I know my age, and then if I take the expected value over the age, then I'm going to just take the expected value. So you say, well, why even bother doing this? Well, because it's actually very useful in many cases. Because it's hard, it might be hard to compute the expectation of x, but it may be much easier to compute the expectation of x given that I know something that I actually don't know, and then I take the expectation over that thing I didn't know. Did that make it any clearer, or maybe less clear? So that's a pretty interesting thing, okay? There's one other thing that's weird and pretty interesting, okay? Okay, this freaks everybody out. The conditional expectation of x given x is x. Because I like to refer to this as what's in a jar of peanut butter, okay? Because what's in a jar of peanut butter? It's peanut butter, okay? Peanut butter is in a jar of peanut butter. If I give you the answer, then that's I'm saying, what is the expected value of x if x is equal to x? And the answer is x, all right? So the conditional expectation of x given y, of x times y given x, is equal to the expected value of y, y given x times x. So you can just take x out. Okay, I'll let you read, we're running over, so I'll let you read the rest. And then the next thing is the commonly used distributions, like the Gaussian and so forth, and try to work the problems. And I'll send you an email on how to hand in the results, okay? All right, good. Thank you.